però me di là. Ha finito.
Hello, good morning. Welcome to our third day of the workshop here, the Ontology Commons Global Workshop, and I am very pleased about the speakers that we have today, and we will be waiting a little bit to start the talks as people are joining the session. So people are being called in from the lounge and also will be joining the session in a minute. And as we are waiting, I will just use the opportunity to share the agenda for the day, which I'm sure you're familiar with. So I will introduce the morning speakers in a minute. We have one plenary presentation and two poster presentations, but just have a look at the rest of the day that will follow. We have two streams today. In room one will be a stream on demonstrators. So Ontology Commons has a number of projects and related projects that really show the ontology-based data documentation. And there's the first one in room one will be about fair technology adoption in demonstrators. And then going on through the day in room one, then the Ontology Commons demonstrators. There's a first round of demonstrators that are, were already part of the setup of the project, and some of them will be talking here, but you can also find more information about the demonstrators. There's quite a few more on the Ontology Commons website, and material about workshops that we already had, and also we had just a closed around a call for another set of demonstrators that we're going to work with in the Ontology Commons project. So join the sessions here if you want to learn more about those in room one from Bosch Technica and others. So we will then have in room two a session which is about sort of engineering and manufacturing and production. In fact, also this will be the topic of the plenary talk, which we'll come to in a minute. So a domain ontology for manufacturing and supply chain in the morning, and then following the lunch break, a session on industrial engineering. Also, please already take a note that we had more poster presentations, and so it should fit in with the program. We have a third poster presentation, short 5-minute presentation after the break in the afternoon, and just before the session summaries, which, as you know, will give you an overview of all of the sessions in a short and concise way. And so far, I've really enjoyed the session summaries. And then in fact, another poster presentation added here also to the program at the end on common action. So please stay on for these sessions in the afternoon. So we see that people are joining, and I think that gives me, so I'll stop the screen sharing here. And without further ado, I think we can introduce our first speaker, the plenary speaker. The title of the talk is Use of Ontologies in the Manufacturing and Production sector. And I'm pleased that we will hear about this topic from Jorge Martinez-Gil, who is a senior researcher and project manager at the Data Science Software Competence Center in Hagenberg in Austria. He also teaches big data and cloud computing at the University of Applied Sciences in Upper Austria. And his areas of interest are building knowledge-based systems that can help solve industry-related problems in a wide range of fields. So I will hand over to Jorge in a minute, but just to also say, if you have questions, please add them even during the session to the chats and ideally to the Q&A, and then we will take these questions at the end. Thank you very much, and over to you, Jorge.
Thank you very much, Gerhard, for the nice introduction. Hello, everybody. As Gerhard has mentioned, my name is Jorge Martinez-Gil. I'm originally from Spain, but I have been living and working in Austria for a long time now. I would like to introduce the place I work for, because it's not very well known in Europe at the moment, but we are trying our best for improving our visibility efforts and so. My employer is Software Competence Center Hagenberg, and we are a research institution that this is oriented to do or to perform research in data science and software science domains. And we are located in the city of Hagenberg, where we have our headquarters, just 20 kilometers in the north of the city of Linz. And our headquarters are there. But also we have a new facility in the Johannes Kepler University campus in Linz, where it's called the Open Innovation Center, where we have close contact with a lot of industrial and company partners. So we are a non-profit oriented institution, and we are just focusing the two subjects I mentioned, data science, software science. And we were founded in 1999 by the Johannes Kepler University. And currently, we are around 90 employees with around 120 if we take into account all the people from partners that are working with us. We have like a revenue of 8.5 million euros per year, and we are an Austrian competence center that gives us an advantages for helping local and regional industry to perform research. We, in this, in the context of our activities, we are very interested in applying, bringing up fundamental research to application scenarios, and mostly because we are located in Upper Austria, that this is a region that this is very focused on industry of manufacturing and production. We have a topic that this is very relevant for us. And as I'm going to explain later, I will try to explain our view why ontologies can help a lot. We are focused, of course, in local, regional, a bit of national industry, but of course, the use cases could be shared across many scenarios. So what we try to do always is to be in a triangle where we have international scientific partners, corporate partners, and us. And we have different relationships with each of them. With corporate partners, we try to apply fundamental research. With international scientific partners, we try to spark students, master PhD students, to do excellent research. And of course, we also try to do some technology transfer. So yeah, the two areas we have, software science, data science. I belong to the area of data science, and of course, knowledge graph, ontologies, and all these kind of things are very relevant nowadays, are getting a lot of traction. And therefore, I would like to explain you a bit of our activities. Okay, so most of my research is currently focused on one project that this is very relevant for the topic of Ontology Commons is the Piane project, that this is funded by the program Interreg, Austria, Bavaria. And what we try to do here is to do a compilation of best practices in the field of artificial intelligence for helping small and medium companies. Small and medium companies are organizations that usually cannot afford to have their own research department, and therefore they need help and they need some guidance in order to find what this is currently trendy and could help them, and to discern what is useful for them and what is not useful for them. And the two regions, Austria and Bavaria, are very focused, or they have economies that they are strongly focused on manufacturing in production. Therefore, this is a real good context for performing this research. So what we are trying to do here is just to help all these, or to facilitate all these small and medium companies to get aware of what is out of there. And of course, there are a different number of branches. For example, digital twins, robotics, and AI-supported modeling, systems engineering, data analysis, application guide for AI manufacturing. The one that I'm going to talk today is going to be inspired by the knowledge representation. I mean, how we can use ontologies for represented knowledge and can be beneficial, helpful for small and medium companies. I want to say that even if we are focusing small and medium companies from the context of Austria and Bavaria, maybe you can get also some interesting insights for your application scenarios or for your specific case. So here in this project, we are a consortium of 5 partners where Software Competence Center Hagenberg is the coordinator, but we have also several researchers and professors from University of Applied Science in Salzburg, University of Innsbruck, University of Applied Science in Kempten, and also the Technical Hochschule from Rosenheim. The project has a duration of 30 months, and we are mostly in the middle, will be concluded in June 2022. If you have, you are curious about things that we are developing in this project, you are kindly invited to follow us in social networks, also to have a look in our websites and so on, so you can be in touch about our activities. And well, said that, I would like to share with you the view that here in SSCH we have about what ontologies can do for the production and manufacturing sector. Okay, so for doing that, I'm going to focus today in a case study on power transformers, because power transformers are a kind of artifact or electrical equipment that this is very relevant in factories, in production facilities. Usually it brings a lot of troubles for keeping track of failures and trying to understand how things are going on. So what we are going to see is going to be an introduction to the problem. We are going to focus a bit in power transformers. I will explain to you, in our view, the 3 major operations that we have identified that we could be beneficial for in this field of root cause analysis and predictive maintenance, that are cost recommendation, that this is a kind of classification technique, failure classification, that this is another kind of classification technique, but that this is usually performed over instances and advanced querying. Finally, we will conclude with major remarks from our view, and also some possible future lines that could be approached in the short future. So yeah, as you can imagine, in the manufacturing and production field, failures are often a very big trouble because they have associated a number of disadvantages, like a big resource consumption in terms of time, cost, effort, and so on, that this is mainly produced by the machine downtimes. Therefore, as you can imagine, there is a great need for tools that can perform a reasonable predictive maintenance, and everything seems to indicate that in the future, this need will keep growing and growing as more data is generated by the industry. However, even there are many techniques for dealing with this ever-growing amount of data, we have the feeling that ontologies have not been deeply explored yet, and therefore there are many gaps that could be filled using ontologies. This is what I would like to bring today, like things that ontologies could be done in this case study. So power transformers, as we mentioned, you have a picture on the screen, is like one of the most essential equipment in power systems, since they allow to assure uninterrupted power supply in installations of any kind, okay? But mostly in factories, production buildings, and so on. However, there is a very big lack of data, proper data to work in this domain from the computer science, the scientist perspective. Is really, really difficult because people, when there are failures, when something happens, they usually don't spend too much time documenting the status of a machine, what happened, the different attributes that could be checked from the power transformer. So it's, for us, has been really, really difficult to find real data we could work with. However, we have been lucky. We contacted some people from Peru, and they really have very good data in this domain, very good data set about power transformers. And we were able to use their data sets for performing our research, for performing our use case. And this was really nice. Because as I mentioned, this is one of the most problematic issues currently, that the lack of real data that we can work with. But solve this issue, we can go a step further, and we can see that ontologies could play a very important role in performing what this is called root cause analysis. By root cause analysis, we understand the capability of having a failure and trying to understand why this failure happened and how we should proceed from the time that we discover it. Okay. Therefore, if you think carefully, there are three major operations could be done in order to act against a failure. One is to recommend the human operator that is inspecting the equipment some possible causes for the failure. Another thing we could do for the human operator is to say we think this failure is of this class. So then in this way, the human operator can have some guidelines, some hints for starting doing the job that must be done. And some advanced querying that would allow to do some prospective queries that could allow to discover the status of the equipment in a given specific time. So if we check into the literature, okay, this is a topic of very strong economic importance. So you can imagine that there is a lot of things in the literature for dealing with these kind of problems. By reading a paper, by looking at the literature, we can classify most of the existing techniques into 4 major branches. One of them is event correlation analysis. I mean, things, events that are correlated is usually because there is a cause behind. Log-based method, trying to analyze the logs produced by the equipment, by the machines, in order to detect patterns that can give us some hints about failures. Execution path mining method that are related to how the equipment was performing and what were the steps and where something went wrong. And dependency graph mining that can be also viewed as a part of a structural learning approach. However, when we were performing our literature study, we realized that there is too little work until date with ontologies. And we wonder why, because in fact, using ontologies is really nice and can give us some advantages and some competitive advantage that others techniques, other methods cannot. And this is what I will try to show you in the following slide. Yes, I am sure that here everybody is very familiar with ontologies, but just as a few hints before starting, I wanted to say, well, we can define very informally, like an ontology, in a very informal way, of course. It's a collection of statements that they are composed by a subject, predicate, and an object, and nodes are usually the way to represent either entities or attributes, while the connections or the relations between the nodes are what this is called the predicates. Based on this definition, we can be sure that subject and object are usually nodes, and the predicates are the vertices connecting. Okay, so one of the most common ways for representing ontologies is the resource description framework format. Of course, there are other formats that are becoming more and more popular nowadays. For example, property graph, with the emergence of all these graph databases like Neo4j and so on, are becoming very, very popular. But for us, we have been working under the hypothesis of representing the data in RDF triples. And this has several advantages from the data engineering perspective, because it allows you to work with a serialization representation of an ontology, and then you can export and work with different formats like Turtle, RDF, JSON for linked data, and so on, in a very, very transparent way, in a very nice way for the data engineer. Also, we are considering that there is a technology called the semantic web rule language that allows to implement the rules very close to human language, and most of the times that allows to perform some inferences, perform some reasoning over the ontologies in order to get things that were implicit there, but to do there explicit. Okay, so why power transformers? Why we have focused? Well, as mentioned, Upper Austria is a region where the industry of manufacturing and production are very important, and one of our key industries is working with power transformers. There are some big companies I'm not going to mention here, but they are fabricating them here in Upper Austria. And as you can imagine, it's a very special component. For the people who are not familiar, could be enough to say that they play a very important role in trying to adjust the voltage and the current without affecting the total power in an installation. Okay, so inside there is a working mechanism. It's not relevant for us because we are studying this problem from a data science perspective from outside. Okay, we are working with the data that this is generated for the power transformer. We don't need to get into the technical insights about this. Even sometimes a bit of domain expert knowledge is also good, but for computer scientists, they have always to sit next to a domain expert, so can tell, okay, this gas is CO2 means that, this nitrogen means that, and so on. It's impossible for a computer scientist to get a total knowledge of the internal working mode of power transformers. So you could imagine that there are different ways to, once that you have the data, there are different ways to proceed for the root cause analysis in this context. And the most popular nowadays is to study or to do a live analysis of the gases that are produced in the power transformer. This is the way it has been done traditionally, and is the way it's mostly done currently in many places. Of course, as you can imagine, this is a very traditional way to operate and have a number of disadvantages. For sure, you need a long time for fault diagnosis, and you need to rely on the individual ability of the human operator. Need to be a very high skill and with a very good knowledge of the problem, and therefore you need big investments in workforce. Therefore, of course, there are associated problems. Once that you have the data, you could think, okay, there are already many tools, many frameworks, many methods for performing classification, clustering, forecasting, all these operations. Some are really, really good. For example, artificial neural network or super vector machines. Why not using them? Yeah, this is 100% clear. With this framework, with this method, you will be able to get really, really highly accurate results. However, even these frameworks have associated a number of disadvantages. First of all, this kind of techniques requires large amount of data in order that you perform a proper training phase. And as mentioned at the beginning of my presentation, data is not very abundant in this domain, in this field. It's really difficult to get real data properly tuned for working with. And therefore, this is a big problem. Okay, second problem is that the resulting model is complicated to be interpreted by human operators. I mean, you can give an input to a neural network. You for sure will be given an output. This output will be very accurate. However, will be very, very difficult for a human, for an operator to understand how it was possible to reach that output. This is because neural networks and these techniques are usually considered to be black boxes. Therefore, it's really difficult to understand how they work internally. And finally, another additional problem is that these results are often not reproducible in the sense that they are dependent of many different parameters, like the number of epochs, batch size, learning rate, or even the optimizer that you are using for calculating the model. Okay, so these are disadvantages that are necessary to be taken into account. And when these disadvantages are not reasonable for the people who need to perform the root cause analysis, then could be reasonable to rely on ontologies for doing several operations. The first of these operations I wanted to mention is like the cause recommendation. What we could do here is to create like a hierarchy of errors. Our way of working should be to take note of the status of a machine, the things we can get it, some concrete values for some attributes that we could get. And of course, with this, we may encapsulate in an object, and then by means of inference, we could locate how this instance of a machine could be classified into the error hierarchy. This is a kind of classification problem. You have an individual, an object, and you need to classify. Of course, this is not so trivial. Of course, you need a domain expert. You need to sit with a domain expert that helps you to do the error hierarchy, to perform the error hierarchy. And then once that you have configured the error hierarchy, you also need to document the kind of corrective actions or the kind of activities you could do once that an error is discovered. Because if we are going to recommend a cause that maybe the power transformer failed because this caused, and then you should do that. Okay. Therefore, this requires also to sit with the domain expert and in order to configure all this operation correctly. However, once that you have it, everything is much smoother, everything is much better, can give a very transparent, a very simple way to try to perform this analysis that we have mentioned several times. Another kind of operation is the failure classification, because ontologies, apart from a terminological layer, they contain a lot of information about instances. So we could use like an ontology in the way the traditional rule-based classifier works. So in this example, we can see on the screen, we see that we have the real data, and we have several pictures of a machine in a given moment, and how the level of the different gases, different levels of water, and so on were at that kind. And we have correctly labeled if in that case the machine was working properly or was wrong, or was having a wrong behavior. So with a kind of knowledge expert, with the help of a domain expert, we could define what this is called rules in order to build a classifier that could help us. And we have done this. We have sitted with an expert. We have been coding several rules with the semantic web rule language, as we have mentioned before. And our surprise is that we were able to get results in line with the best techniques based on random forests, in key nearest neighbors, and so on. If we, of course, we didn't try the best configuration possible for each of these methods, but just a simplistic comparison tell us that we are able to get a really good results in this field, and with no complicated neural networks and so on, with a model that this is highly interpretable, because almost everybody can understand rules that they are of the kind if then, okay, with maybe some additional constructor, but still quite simple to be understood by a person. And finally, is the working with ontologies gives you the capability of performing advanced query. When you are documenting your processes in plain text, this is usually not a good idea. Of course, it's a very cheap way, and it's the most intuitive and more natural for people. But then queries over this documentation will be difficult and will be almost impossible. With working with ontologies gives you the advantage of that you can use a kind of graph-oriented language for performing queries. And of course, this has a learning curve. It's not a query language that this is very intuitive to master at the beginning, but with a bit of patience and experience, it's possible. You could do, or you could perform queries that are much more complex, that can give you better insights than just using traditional way of documenting things with plain language. Okay? So in many cases, documenting your equipment, the cases that you were facing in the past, and so on, with a proper ontology model will facilitate some kind of a query in the future. So, saying that, okay, I don't. The time that we have for this talk is limited. Just I wanted to make a compilation of the major hints, of the major pieces that I mentioned here. Is when working with power transformers, if you are willing to work with ontologies, you will be able to have a systematic way to build tools for root cause analysis, that this is outside of the context of the other four methods, traditional methods that they were done before. You will have powerful inference reasoning mechanisms in order to work with the ontology at two levels, at the level of the T box and at the level of the A box. Most probably, and in many situations, will be a very smart way to document your industrial component and processes, better than having, for example, plain text. The advantages of using these ontologies is that you won't need large training data sets for your data. Okay, this won't be necessary anymore. You will have a full interpretability of the model who you are using. You will be able to be interacting with a model that this is like a white box, and where you can understand why the outputs are generated, and you won't have issues adjusting dozens of parameters for getting the model to work. Okay, as disadvantages, the disadvantages are also important. Okay, is that currently there are not good user interfaces to work with ontologies in this industrial domain. This needs a lot of patience and good thinking and a good design in order to bring it, because it's something that has not been too well explored yet. You will need domain experts, and the bad news is that the domain knowledge that you are getting from these experts will be difficult to reuse in other problems. I mean, an expert could help you to write the rules for the rule classification or to construct the hierarchy of errors. But then this knowledge that is provided to you will be difficult to be reused in other situations. And this, of course, is a serious disadvantage. And of course, will be also some learning curve for human operators to manage, to master these techniques based on ontologies, because are not trivial and needs some experience and patience how to perform languages in a graph-oriented language and so on. But of course, I mentioned before, once that you master, you will have a competitive advantage that wouldn't be able to be reached before. And yeah, that's all. I think this is like an overview of what I wanted to talk today. It's like my view, or the view of my team of how ontologies could benefit manufacturing industry that are not done before, why are not done, and what could be get if you do it. Now, that's all from my side, but I will be very happy if you want to ask me some questions, to have some discussion, because maybe there are things that are interesting and you would like to get into more detail. So thank you.
Gerhard, there seems to be a problem as we cannot hear you.
Yeah.
Now, yes.
Thank
Thanks.
you. Yeah, thank you very much. Sorry, I will say again, yeah, thanks for this fantastic presentation. That really gave us a sort of everything in the application of ontologies right from the beginning of using other methods to the application and to all of the advantages, disadvantages, and so on. I have many questions to discuss, but we also have questions here from the audience. Can we post them in? Do you have already an order of the questions? That then we start with that. Yeah, okay. So thank you for the presentation. Are there any hyperparameters for the semantic web language algorithm? Are there any evaluations?
More than accuracy. Yeah. This is very good questions. Yeah, the semantic web rule language should be properly tuned. However, the basic configuration, the one that will allow you to perform as a general purpose rule-based classifier, is quite simplistic and quite easy to configure, because you have production rules where you have an antecedent, a consequence. The antecedent can be composed by several operators like and, or, not, and so on. So things can become more complicated, but in principle, for operating at the basic level, the hyperparameter tuning wouldn't be a problem. Other ways that for calculating the quality of the model, just far from accuracy, of course. This is, we could have like model the problem as a retrieval problem. We could go to retrieval measures like precision accuracy, precision retrieval, F measures, and so on. If we model the problem in another way, this is not a problem, just like any other rule-based classifier could be. The thing you could do even a rule-based classifier, but having everything integrated within your ontology, within your framework, is an advantage.
Mm-hmm. Thank you very much. That's already also, I had this this question myself about the rule-based classifiers versus because you basically comparing it with expert systems, right? And you already now mentioned the advantages here, which is great. So let's go to the next question then. Thank you for the nice presentation. Did you observe a pro for the operator's daily work?
Yeah, this is a very good question. Like I mentioned before, the learning curve is very tough. It's very complicated. The people are not very keen to work with ontologies at the beginning. You need some education, some to convince them that this is good for them. From a strategic point of view, the advantages are clear. From the operative, it's more difficult. I think this would be possible when we have better user interfaces, the graphical user interfaces that this is not the moment. So a daily pro is difficult to think about, but it's matter of keeping exploring and convincing people that this has, in the long term, advantages that wouldn't be reached by other. For a person, it's much easier to use the black box. I mean, you give an input, you get the output, and that's all. But having insights about what happened inside the model could give you a different perspective for helping you in the task. So no, the short answer is not, but hopefully with better user interfaces, with more pedagogy, and with other use cases, we will be able to.
It would be also great to capture that, as we talked about from the project, about our roadmap. These types of gaps, right? We want to really highlight them for what are the needs really to make the impact greater, and I think that's a fantastic, very important point that we also heard in other presentations. So we have time for some more questions, and we had another one here from Tobias Köhler from DLR. Thank you for this presentation. On what basis are the semantic rules modeled? Do you use experimentally determined data for this?
Well, the rules can be generated in two ways. You could you could mine the rules automatically and derive them from the data. However, this is not exactly what you want, because if you do this, you are not using the full capability of the expert for helping to build the model. But you could theoretically mine the rules using some kind of mining technique. Okay, you have the data set and you can mine the rules exactly like other kind of data mining technique. But in this case, we sit with an expert and they tell us, oh, this is a high level of nitrogen. This is the equipment, the power transformer is not working. So reflect this by means of a rule. So when the expert helps us to tell what is high level of nitrogen, we can create a rule where we say it's a high level of nitrogen. This is not working. So we sit with the expert and he tells us how we should proceed. Okay, he's giving us in order to code. And like the rules are so easy, are of the structure if then, for the expert it's not easy. It's not difficult to communicate with us what it can do. At the end, we are having a kind of random forest, because we are having if then that sometimes don't came from a same root. So it's not surprising for us to get the same results at a random forest, because at the end it's quite similar.
You touched upon also sitting with the expert here about another topic which we're discussing, and I'd like to get maybe another time your experience on, is what we call the translation process, right? So sitting with the expert and translating that into the implementation. But we also have another question here from the audience in the chat. That one exactly. Have you considered grounding your failure modes in an international standard? The words used to codify failure modes are often not clearly differentiated.
This is a very interesting question, and I think something that this is missing. At the moment we didn't work with international standards, but this could facilitate a lot the task of the data scientists, of the application of ontologies, because at the moment there is work on programs but manufacturers are not very open to this in the moment. However, convincing them of using international guidelines for failures could improve a lot interoperability and could spark development of these kind of solutions to another level. This is clear. Unfortunately, at the moment, we are not using that.
Thank you very much. I mean, lots of interest. There's some more chat. Please join the chat as well with any responses for the other chat questions and so on, because we have to move on in the program. But do get in touch with Jorge and also for you to get in touch with the other people here asking questions. So thanks again for a fantastic presentation, and I'd like to now invite our poster speakers. First of all, Athina Kritsotaki, who is a graduate of the Department of Archaeology and Art History of the National Kapodistrian University of Athens and holds a master's degree in computer science. Her scientific interests are focused on knowledge representation, conceptual modeling, theory, ontology engineering and development, archaeological theories of prehistory, and argumentation systems and reasoning. She has been working in cultural documentation and development for the Center of Cultural Informatics in Forth for over 15 years, and we look forward to this poster presentation.
Hello everybody, I'm Athina Kritsotaki, archaeologist and specialized in cultural informatics, and I have been working in ontology engineering for 17 years. Let me share the poster for you. Okay, just give me 1 minute. I suppose you can see the poster, right, everybody?
Yes, yes.
Okay, I will present you the SCHOCro ontology we developed here in Forth in the context of the SCHOC European project about social science and humanities open cloud. And basically, the acronym of the model is the acronym of the project. The SCHOCro reference ontology is a common meta-level schema which is used as a top-level ontology for organizing knowledge and information across various sources of information in the social sciences and humanities open cloud. Basically, it intends to provide a semantic interoperability framework for the description of the SCHOC data lifecycle in the social and humanities domain. So in order to achieve this goal, we went through several steps. For example, we started bottom-up methodology, and we consulted first the SCHOC data providers. And then we started developing the model, and we actually implemented in RDFS format. And then another step was to do mappings, transformation between selected metadata standards that the SCHOC community uses to the SCHOCro ontology as a target. And this was done as a proof of concept for our model. And the final step is to update and finalize the ontology, which is an ongoing activity. Still, the project hasn't finished yet. So, SCHOCro practical use, as we said, it is a workflow model that aims to describe the full data lifecycle in the social sciences research. So, the scientific data cannot be understood without the knowledge of the circumstances under which they were produced. SCHOCro is built on the ground of the analytical methods used in the various disciplines in order to inform a common workflow that captures all relevant scientific activities used. Another practical use of the ontology is that the intention is to document the provenance of knowledge in every step of the knowledge chain, which allows to trace the intermediate results, the data of the process that produces data. It enables us to capture the tools, the services, the parameters used at each point of the stage, the data that generated, how and by whom they were generated, the inputs and the outputs, not only the activities. And this model uses and extends the SCCH ontology, which is an ISO standard, and it is an event-based ontology following the event-centric approach of the digital provenance models. It can be used for building huge networks of knowledge and can answer complicated questions of type of who, when, where, when. Basically, SCHOCro can be applied as a standard in order to implement metadata descriptions for tracking the data lifecycle in individual projects, institutions, or disciplines. It can be used as a common language between social science and humanities researchers with IT specialists. And the thing that it is encoded in RDF, it is helpful in order to be used for mappings, transformations, and integrations existing data across projects, institutions, into interoperable semantic repositories of information for reuse and further exploitation between social research communities. And this is something that agrees with the principle of FAIR. And you can find more information about SSHOCro. You can see in the poster on the website of the projects. And this is what I have.
Thank you very much. Thank you. This is very useful as well.
Welcome.
With more information obviously we don't have time for questions and answers here, but please join the chat again and use the questions and answer possibility there. And also, as you know, there's the lounge. So if you want to take a table at the lounge after the session in the coffee break, then that also gives an opportunity for people to meet and have questions. So thank you very much for that presentation.
Thank you too.
I would like to then invite our next poster presentation from Fabio Piane, who has a bachelor degree in maths from the University of Bologna and a master's degree in computer science. Also, this was in the area of systems and networks. And he's has a PhD scholarship at the University of Bologna, where the project is about the integration of data science and machine learning techniques in the classical computational science, particularly in the realm of material science. So, the intrinsic complexity of the field is of interest to him regarding the strong foundations in knowledge representation theories and data organizations. The work on ontologies is now a fundamental part of the research. So please, Fabio, take the stage, and look forward to your poster.
Hi, can you hear me?
Thank you. Yes, very good, very well.
Okay, I'm now trying to show you the poster. Can you see that?
Yes.
Okay, perfect.
Very good. Thank you.
Yeah, thank you. As you already said, my work shifted towards the development of new ontologies, and in particular, the one I'm presenting you here, which is MAMBO, which stands for Materials and Molecules Basic Ontology. And we developed MAMBO in order to find standards for the representations of materials, molecules, and related domains in the realm of computational science, and for integrating computational science with the experimental workflows. This endeavor started from quickly day life problem we faced here in our institute in Bologna, because we had our time communicating with our colleagues, which does experimental workflows and research. We had problems understanding what they are doing and what they are struggling with. They had problems understanding what we are doing and what we can actually do with our research in the realm of computational material science. So we developed MAMBO in order to integrate these two different workflows. We paid particular attention to the nanoscale, which is the main core of the research activities here at the ISMN in Bologna. But of course, we tried to let MAMBO to be as general and as generalizable as possible, and in particular to be able to represent the entire realm of material science. Of course, MAMBO is still a work in progress, but as already said, we expect it to enable the systematic integration of computational and experimental data in the realm of material science. And in particular, we put strong emphasis on the application of data-driven frameworks because, as already said, it's my main background, and my PhD thesis revolves around the application and integration of data-driven frameworks to material science which means, of course, the realization and the ordering of data and their usage in techniques like machine learning and artificial intelligence in general. Here we can find the two figures, the first being this one, representing the two main hierarchies of MAMBO. As you can see, our material is represented as we can see the sum of its properties and the structural characteristics represented by the structure class, which has deeper hierarchies relating to the different subparts that compose a material, which can be molecular systems, which are, of course, molecules or molecular dimers, etc., circular units, particles down to the atom. And in particular, we found different main, we can say, entities in the realm of structure, which are molecular aggregate, which is our real core in the development of MAMBO, and is the main concept we want to represent because we found out that these kind of topics have been left out from the main ontologies, the previous ontologies present in the realm of chemistry and science in general. And of course, we focused on that, but you can also see that we left space for the crystal concept, which is an example of how we aim to relate to different pre-existing ontologies like MO and in particular in this case MDO, which has been a strong inspiration for the development of MAMBO. Going on, the second figures relates to the hierarchies of the material property and in particular the two classes of measurement, which represent the experimental workflows, and calculation, which instead represent the realm of computational science. As you can see, they are quite, these pictures let you see how symmetric the hierarchies are, and in particular how measurement and calculation both shares are related method class, which will be able to gather all the parameters of different workflows and experiments to represent the different kinds of techniques, being them in the experimental realm, for example, of the optical method or electoral method, or in computational sciences, something like DFT, molecular dynamics, and kinetic Monte Carlo calculations. We aim to represent the two different methods in order to be able to, of course, if you like to separate them or having the small details in different experiments, you will be able to do that. But if you just like to know as much as possible on a specific property of a specific material, you can just integrate flawlessly the data coming from different realms and different procedures. This is done both in order to be able to, as I said in the beginning, to speak common languages between between experimental researchers and the computational researchers, but also in order to gather as much data as possible for the application of data-driven technologies, because one of the biggest problems we had, aside from the lack of standards, is the fact that quite often we found out that using only one source of data, being that the experimental or the computational source, led us to having too few of data in order to actually empower stronger methods like deep learning and neural networks method, and we have to rely on simpler methods and algorithms which are less powerful but can be trained with less data in a quicker way, we can say. So thank you. I'm afraid I am out of time, so thank you for the time and for the interest.
Thank you very much. Many things to discuss, obviously, from our perspective. But again, maybe we can have a chat also in the lounge or something like that, and please ask your questions or send us a contact and so on. So thanks again for the speakers of the session this morning, and we will now have a coffee break. But also I would like just to correct, I think just to say I didn't say that correctly. I think earlier, after the afternoon break, there will be another plenary talk first and then a poster. So this will be about this one of the big ontology developments, the fiber ontology, and to hear about the lessons learned from that development. So we're looking forward to that, and in the meantime, of course, the other sessions. But for now, thanks again and enjoy the break. Thank you.